Our next experiment will again be on optics, and we will be finding out the focal length of a concave mirror. Now, as all of you know, concave mirror is a converging mirror. We will be using an object. This basically will be in the form of a needle. It will be sending two rays towards the mirror. One is this. It will go from the focus after reflection, and this, which initially is coming from the focus, will follow a parallel path and will try to meet the first ray at this point. Now, obviously, whenever two refracted rays appear to be meeting, they always will form an image. Now, if this is the object, in the same fashion you will be getting an inverted image of the same out here. Now, you will be wondering that if the image is this, what is this standing for? Now, this is again a needle known as an image needle, which is used to locate the image which is there right above it. The reason being, the image is although real and inverted, I can see it, but I cannot locate it unless and until I use another needle to get its direction on the optical bench. Now, in order to find out the focal length, the formula which I will be using is the basic mirror formula. 1 by V plus 1 by U is equal to 1 by F. This being the image distance, this being the object distance, F being the focal length of the mirror that you are using. Now, U will be obtained from the distance between the object needle and the mirror. By the mirror, I mean the pole position. Similarly, the image position V I can obtain by this distance. Now, after conducting this experiment, I will only be having V and U values. Either I can solve for F analytically, or I can use even the graphical method. Here you can see that we have a graph of V versus U readings. Now, can you tell me why I have used a minus sign along with them?
Because it is being formed on the negative axis. X and Y value that we have on the axis is negative. We have taken negative axis exactly.
Okay, and the reason for getting U and V values is because of the sign conventions that we follow in optics. Now, you will be getting a graph of this shape. Once you plot this graph, you can easily bisect it, and the point where the curve is bisected, you can see what is the corresponding value of V and U that you are getting. Now, once you get V and U values from the graph, obviously you can substitute them in the formula 1 by V plus 1 by U to obtain 1 by F. When you invert this, you will be getting the focal length. Mind you, all these distances we have taken in centimeters. Similarly, another way to calculate focal length will be plotting the graph between 1 by V and 1 by U. When I plot it, I get a straight line intersecting the x-axis at this and y-axis at this point. I will be using these 2 points, basically 1 by V and 1 by U, to find out the focal length. Now, what we say is that this point 1 by U gives you the focal length. Can you tell me why I have straight away said minus 1 by U to be equal to 1 by F?
Ma'am, this is because at this particular time, ma'am, the value of one of the variable is non-zero, whereas the other comes to be equal to 0. So,
okay,
when we put it in this formula, we directly get the value of 1 by F.
That's absolutely correct. On this axis, I have 1 by U, but 1 by V comes out to be 0. So, when I substitute it in the mirror formula, I straight away get 1 by U to be equal to 1 by F. The negative sign only indicates the sign convention that you are taking, and since this is the formula, focal length will obviously be coming in negative. Now, following this ray diagram, we will try to do this experiment on the optical bench. Basically, we will be using U and V values. Now, this is the optical bench which has readings till 1 meter inscribed on it. This needle, as you can see, is the object needle. This is again an image needle. Now these two can be interchanged, and since these two look alike, I am using a small paper flag along with this needle to differentiate it from the next needle. You are free to choose any one of them as the object or the image needle. Now let me show you the main boss of this experiment, which is the concave mirror. You will be able to see this mirror now. This is a converging mirror. It will be giving us the inverted images. Now we will be setting it to find out the value of center of curvature, because we want to find out the value of focal length. Before doing that, it is very necessary to remove the parallax error from this experiment.
Excuse me, ma'am. What is parallax?
Now basically parallax is a kind of error in which if you try to see from this side towards the object and the image needle, there is a relative shift. One appears to move slower than the other. So this is said to be parallax. Ideally they should be moving at the same speed at left or right as you move your head. Now the reason why we want to find out the focal length is that I always have to work away from the focus in order to get the real images, because within the focus you will always get a virtual image which cannot be seen by any screen or by any image needle. Now when I be reaching the position of C, I will be getting its image at C itself. Now in the view of the camera, you can see the object needle. Now if there is a parallax, you won't be able to see its image exactly tip to tip with this needle. It will be either left or right from the object, and it can be clearly seen if you try to move your head away to the left or the right from the object. Let us try to see what parallax looks like. Now this inverted image represents the image of the needle shown below. Now ideally it should be tip to tip with the below needle, but if there is a parallax, you can see it moving either to the left or to the right from the object. Now this image has been seen going left or right. Ideally this should not happen. Both the object as well as its image should move together, either to the left or to the right. In this case, you can easily see the parallax. There is a gap between both the tips. They should be looking exactly one over the other. Now in order to take the further readings, you require to know the value of focal length. Focal length can be calculated from the center of curvature, which is double of it. The object, if it is placed at center of curvature, the image is also formed at it. The reading which is currently set on the optical bench has object placed on center of curvature. Side by side, you can also assure yourself that there is no parallax in this reading, because the image is exactly over the object needle, and even on moving your head left to right, both of them shift together. They are not separated in relation to each other. So this is the reading of center of curvature. Now having removed the parallax error and having found out the value of focal length, we are using these two uprights. This will be acting like your object, and this needle will enable you to locate the position of the image. Now since both of them look alike, I will be using a small pointer in the shape of a paper flag in order to discriminate object from the image needle. Now I have to take the object needle well away from the focal length of this mirror, which I have just now determined. Can you tell me why I can't take this object needle between focus and pole of the mirror?
If we take this needle between the focus and the pole of the mirror, we will get an inverted image. That is, we will not be able to get the real image. So we try to keep it as far as possible.
That's absolutely right. Now at this position, you can very well see that the tip to tip alignment of the object over needle and the image over the object is there. You can see the two images. In each of one of them, object over image and image over object can be seen. Even if you try to move left or right, this tip will not leave the other needle. It means there is no parallax. And finally, the two positions, that is the object needle and the image needle, will give you the object and the image distance respectively. Now, after doing the experiments, we will tabulate our readings in the following manner. The first column, as you can see, is of the position of the mirror, which will be remaining constant throughout the experiment. The only thing that you can change is the position of the object and the position of the image. As you change the position of the object, obviously you get different values of I for the same value of mirror reading M. Now, in order to find out the object distance, you subtract the position of the object from the mirror position. Similarly, to get the image distance, you subtract the position of the image from the mirror position. Now, having received the value of u and v, you can substitute them in a formula in the last column, 1 by u plus 1 by v, and you will be obtaining the inverse of focal length. If you re-inverse it, you will be getting the focal length of this mirror in centimeters. This is by the way of readings and taking the average that you received the value of f. The same can be done even using two graphical methods. Let us see how is it possible. Now, this graph shows you a plot of v versus u readings. When you get the similar points as per shown, you can connect them using a smooth freehand diagram. Once this curve is obtained, you can bisect this using a protractor or making a 45-degree angle like this with the very first square, and you will be cutting this curve at a particular point as shown in this graph. From this point, you can drop down two perpendiculars on either of the axes, which will give you the value of u and the value of v, which can be further used to find out the value of focal length by the same mirror formula. 1 by u plus 1 by v is equal to 1 by f. Using this formula for the given values from graph, I receive the value of f to be 18.3 centimeters. Similarly, the next graph, which shows you a plot of 1 by v versus 1 by u, comes out to be a straight line. Now obviously the straight line would be intercepting the x and the y axis at some points. Either of these points can give me the value of focal length. For example, I have taken the value of this intercept, which is 0.0285, and found out the value of focal length. 1 by v is equal to this value, which again will be equal to 1 by f. U is 0 here because on y axis it will be 0. Focal length from this method comes out to be 18.3 in this case. Like this, we can find out the value of focal length by three different methods, one by averages and two with the help of graphs. So we are through with the experiment of finding the focal length of the concave mirror.